In this and the next video, we shall talk about distribution of quadratic forms. By a quadratic form, we mean a function from Rn to R. So it's a quadratic form in n variables such that an arbitrary vector x in Rn is mapped to x transpose Ax. So this one is 1 cross n, this is n cross n, and this is n cross 1. So the entire thing is 1 cross 1. So it is indeed a scalar. Now here we shall put the further restriction that this matrix A will be a real symmetric matrix. We have already seen how such forms occur when we deal with variances. So in this and the next video we shall discuss about distributions of such things. In order to talk about distributions, we need some random variables. So this little x will be replaced by a capital X vector, a random vector, which we shall assume has multivariate normal 0i distribution, which basically means that its components are IID normal 0, 1. And we shall also be given a real symmetric matrix A, and we shall be interested in the distribution of x transpose Ax, which is a real valued random variable. The first and the most important theorem that we are going to discuss starts with our background setup. X is normal, multivariate normal 0i, and A is a real symmetric matrix. We are going to put one more assumption on A. If A square equals A, that is A is idempotent, then x transpose Ax will have a chi-square distribution. So I need to specify the distribution of the degrees of freedom, and that will be same as rank of the matrix A. So A is assumed to be both real symmetric and idempotent. Then this quadratic form will have chi-square distribution with this particular rank. The proof uses an important fact from linear algebra. It says that since A is an idempotent matrix, hence A can be written as A equal to P transpose I 0, 0, 0, where P is an orthogonal matrix. So once you can write it in this form, x transpose Ax becomes x transpose P transpose I 0, 0, 0 Px, and incidentally when I wrote R, I meant R is rank of A. Now once I write it in this form, it's only natural that I will call Px by a new name, call it Y. Then replacing this by Y and this by Y transpose, we get. Now this is a quadratic form in Y, but since here all the diagonal entries are like 1, 1, 1, 1, the first R of them, and all the rest are 0, this quadratic form is simply summation yi square, the sum going from 1 up to R. Now observe that the distribution of y can be very easily obtained. X follows normal 0i, so what can you say about the distribution of y? That will be again multivariate normal n, 0, it will get multiplied with p, but that will keep it 0. Then the covariance matrix will be, your original covariance matrix was I, you will pre-multiply it with p and post-multiply it with p transpose. But since identity matrix can just be dropped from a product, it is same as p transpose. But p being an orthogonal matrix, p transpose is just identity. In other words, you find that y is also have the same distribution as x. That means the components of y are IID normal 0, 1, and you are adding r of them after squaring. So this must have chi-square with degrees of freedom r. And that concludes this proof. We had this theorem. This was the background information, and if this was given, then we can conclude this. Now we are going to do the converse. This will be given and we want to conclude this. More specifically, I will take this up. If x prime ax follows chi-square with some degrees of freedom r, in that case, we must have a idempotent and rank of A should equal that R. The proof of this will require spectral decomposition of A. A is real symmetric matrix, so I can always decompose it as P transpose dP, where P is orthogonal and D is a diagonal matrix. So much as in the last proof, I can write my quadratic form as a quadratic form in Y, and we have already seen in the last proof that Y again has distribution same as that of X. So essentially this argument shows that I can assume that this matrix A is without loss of generality a diagonal matrix. Now since D is diagonal, so Y transpose dy will be of the form summation di yi squared, where di's are the diagonal entries of my capital D matrix. Now observe that rank of D is same as rank of A. I still do not know what rank of A is. I am going to show that it is equal to R. So right now I can say, suppose rank of A is equal to K. So only K of the diagonal entries of D will be non-zero, the remaining will be 0, and I can assume without loss of generality that the non-zero K things will be the first of the K di's. So this sum will go from I1 up to K, because the remaining things will not contribute anything. So we have summation di yi square, I going from 1 to K, has chi-square with r degrees of freedom. Now I have just now mentioned that the y vector has the same distribution as this, so the components of y are IID normal 0, 1. As the result, if I square them, then they will have all chi-square with degrees of freedom 1. So I am taking a linear combination of r independent chi-squares, each with degrees of freedom 1. Now it is pretty difficult to work with its density or distribution function, so we shall work with its characteristic function. So from standard property of chi-square distribution or gamma distribution, this will be the characteristic function of each of the yi's. So we can directly write down the characteristic function of that. It is this expectation, the characteristic function of this. So I just write it as product. Now since the yi square are all independent, so the expectation will split, and I quickly recognize that this is nothing but the characteristic function of yi squares, that is this, but in place of t I have t times di. Same thing, but in place of t I am writing t times di, and right now I notice that there is a little problem. I am using I for the complex I am also using I as my index. I should better not use I for the index, I will call it j. So j going from 1 to k. Similarly here also I will make this j, make this j. Now this is supposed to have chi-square r distribution, so this characteristic function should match with the characteristic function of chi-square r, and that is 1 minus 2it to the power minus r by 2. So we are getting this equality. So we have this thing. I will just square both sides, so get rid of that half. Well, take reciprocal of both sides, so make it r and make it 1. So now you see that on both the sides you have polynomials in T, and remember this has to match for all T in R. So two polynomials are matching over all T, so obviously their degrees must match. Here I can see that the degrees are, and there you can see that the degree, because each of them are linear, degree is K, so immediately you can get that K must be equal to R. K was rank of A, so I have shown rank of A must be equal to R. Also, if you match the coefficients of the same power of T on both sides, you will get that all the D's must be equal to 1. You can sort of see it easily, because once you set all the things equal to 1, you exactly get the same thing. Now the spectral decomposition of A that we had started with was of the form P transpose the D matrix times P. Now I see that all these things are 1, so this is basically the nice identity matrix. These are anywhere 0, 0, 0. So A must be of the form P transpose I 0, 0, 0 P. P is orthogonal. Any such matrix is an idempotent matrix, so A must be idempotent. And that completes the proof of this theorem. In this problem, we start with x1 to x5 IID normal 0, 1. I tell you that there is a certain linear combination summation AIXI such that its square happens to have a chi-square distribution with some degrees of freedom R. I do not tell you what AIs are. I just tell you that this has chi-square distribution. Just based on this, you have to tell me what must R be.